We have a long oil pipeline, 100 kilometers long and the diameter of 20 centimeters that initially is at 20 degrees C. So oil at 20 degrees C is just flowing through this pipeline and it is surrounded with air at 0 degrees C. What happens here is at a specific time, let's say time 0, the pump is shut down, so we turned off the flow and the pipeline and its content starts to cool, begins to cool. And what we have been asked is the pipeline temperature at after 4 hours of this turning off of the flow, and the second one is the time at which the oil and the pipeline by content its contents reach to 1 degree C. So we have this oil pipeline and it is surrounded with the air at 0 degrees C. So what we know here for this problem, known our initial temperature is 20 degrees C of the pipeline with oil. T infinity is 0 degrees C, and H for air is 10 watt per meter square Kelvin. Now, in terms of bulk properties, it's transmitting fluid. So we're going to assume the thickness and fluid and everything else together. The density is going to be 900 kg per cubic meter, or you can assume only the oil that is flowing through that, and C is 2500 joule per kilogram Kelvin. We're going to find temperature at T 4 hours and the time when the temperature reach to 1 degree C. Assumption is on a steady state, no generation and no radiation here. Constant properties. And assuming that the pipeline by itself is made of very conductive material, then we can neglect the resistance of the conductive and we can assume only like oil exists here for the purpose of this problem. And the other thing, let's say K is not given, so we don't know the K of this system. So for now, K is not known. So typically the first things that we do, we evaluate the Biot number, but here let's assume Biot number, which is H V over A divided by K. Let's assume this is less than 0.1. And the capacitance model is valid. So what we can say here is T infinity, Ti minus T infinity. If that assumption is valid, then we would have minus HA over rho VC T. Okay. And here the T infinity is 0, Ti is 20 minus 0, so equal to exponential of minus H is 10. The surface area is pi times T times 100 times 2 power 3. And this is going to be 900, 2500, 2 square times 100 times 10 to the power 3 times T. So if you do the math, T would be 20 e to the power of minus 888.889 times 10 to the power minus 5 T. Now we can find the two quantities asked. First, A at T 4 hours, which is 4 times 600 second. If you replace their temperature at 4 hours would be 5.6 degrees C. This is temperature at T 4 hours. For part B, we put T 1 degree C in the above equation, then what we are gonna get, T is gonna be 33700 second or 9.4 hours. So it takes 9.4 hours for this pipeline. When if it shut down, there is no oil flow, nothing. It just acts as a solid, and the temperature, as you can assume, acts as a solid, and the temperature drops from 20 to 1 degree C. Let's check the file number. So the number is HV over A, K, which is gonna be 10. This is gonna be divided by 4, and K 10 times 0.2 divided by 4, K, or 0.125 K. You wanna have that to be less than 0.1. From here, K should be greater than 1.25 watt per meter Kelvin. If the material that we have, the overall material, the oil that we have, has a thermal conductivity of greater than 1.25 watt per meter Kelvin, the assumption is correct, everything is fine. Now let's assume we have gone to the lab and we have done the measurement, and we know K typically depends on the type of crude oil, but for crude oil is in the range of 0.15 to 0.21 watt per meter Kelvin. Therefore, what we are going to get for the bad number is going to be from the range of 0.83 to 0.625, which are greater than 0.1. And what it means here is our answers are not quite valid. So the answers in A and B are not quite valid. They give you some approximation, they are very approximate. Actually, they are more, I would say it, approximate than would like them to be, or we would hope to. And in order to increase the confidence, let's say for this pipeline, when we could use to increase the confidence in the answers that we are getting, the diameter should be about 0.025 meter or less. Of course, this is not feasible for already existing pipeline, but if you want to use the LOM method for a pipeline of oil with the 20 centimeters, with the conditions that we've specified here, then that's not going to be like a valid assumptions, unless that, let's say, the H, the heat transfer coefficient of air, also if it's less than 10 watt per meter Kelvin, then again, there is an opportunity for using that or getting a more confident type response from the lump capacitance assumption.